and today we want to talk about two things. The first one is in the steps for design. The first step, as we saw last time, is let me go there. Is the computation of design moments. Let me just show you that. So after it's here, it's just right here. Exactly. The process number one is the determination of design shear force and bending moments at critical points on the element. So let me even pick that one and bring it down here. I believe you can see my screen well. So we already have a question that we're going to use, but let me have a new slide here. Okay. Sorry. The determination of design shear force FV and bending moment at critical points of the element. So, want to look at three kinds of beams. We're going to analyze a simply supported beam. The first one is a simply supported beam with a point load. It will look like this. So, and it has a point load. Simply supported beam with a point load at the center. Okay, exerting a force W at the center of the span. So if the span is L, sorry. Let me log in with another gadget just to assess. So if the span is L, okay, if the span is L meters, then what will be the load? We need to find A, B. We have a reaction at A, we have a reaction at B. What will be the reaction at A if this is L over 2 and this is L over 2? Somebody just unmute. I know this is not new to you. If they are equal, what will be the reaction at A? Ayub?
It will be RB times L
RB
plus
times
RB times L, the entire span, then plus W times L over 2. Yes, like that.
Wow. I think you're approaching it from somewhere. However, I think you're trying to use the sum of moments method. But this is very direct. That if we have a load at the center, then equal amounts will be distributed at supports. So it means RA will be equals to W over 2 and RB will be equals to W over 2. Sawa sawa. RA will be equals to W over 2. RB will be equals to W over 2. Okay, what if we draw a shear force diagram? Let's bring it here. So we have our free body diagram here. I think I had a ruler. So if we draw a free body diagram, we have A with W over 2, then we have W over 2, then we have W. Though these are free body diagram. We can do this. Okay. So these are, what about our shear force diagram? It will be in this manner. Sorry about that. Shear force diagram. So we'll have it increasing by W over 2. Then you have it maintaining a constant W over 2, dropping by W over 2. That way, isn't it? I think we know that. So this will be a distance L over 2, L over 2. And we said that moments will be positive, or rather moment will be maximum moment. Yes, Tom, you want to say something?
Yeah, can you repeat on the reaction?
I repeat on the reaction.
Yeah.
Wow. Whoa. Sorry. So, okay. Yes, Godfrey?
But we can't see that end very well.
You can't see that end. Unzoom the screen, Unzoom the screen. Unashika screen una unzoom hivi inakuwa unaona vizuri.
Sawa.
Can you try that?
Yes, let me try, sir.
Just try now and let me know. You just do it as you are talking. Is it okay?
Yeah, it is okay, sir. Thank you.
You're welcome. Okay. So, wow, mmesahau kuchora shear force diagram, you guys. So, if we have an upward reaction at A, then it means that there will be an instant increase. There will be an instant increase by W over 2 to the positive, which will be maintained throughout the span up to the point load, and then it will reduce by W, because that's where we have W, and then also maintained and then increased. Okay, so then that is SFD. So this is W over 2. What about the BMD? Now drawing the BMD. Okay, you can see my page is small, so I'm just going to use this section that I have. Okay, so this is A, this is B. Okay, so we are saying that maximum moment will be developed at zero shear. at the place where we have zero shear. Okay, and not really any place where we have zero shear, but specifically where we are changing from positive to negative. Okay, because you realize at some point you might have at the starting points and the ending points having zero, but we are talking specifically of where we are changing from positive to negative, meaning this point. So at this point we will have maximum bending moment. And how is the maximum bending moment going to look like? How is the maximum bending moment going to look like? So where we have a positive shear force, we are going to have a negative bending moment in this way. So we said in the design analysis that where we have a point load going linearly, then it's going where we have a point load, then it's going to vary linearly. Okay, it's going to vary linearly. So it will be in this way. Okay, and it's going to be negative. Okay, that is something that, so the main essence of us doing this one is for us to obtain formulas, because hatutakuwa tuna calculate hizi vitu tunachora ndo tuweze kudetermine the shear force FV and M at critical points. Okay, just a bit. Let me just look at this. Okay, so what are we saying? That we have determined that we find FV for this case will be given by W over 2. This is very important. Equation 1. How will we find the moment at this point? Because that's what we want. It's what we call the maximum bending moment. The maximum bending moment will be given by the area under the shear force diagram. So M will be given by, what is the area of this point? Somebody to calculate the area and tell me. Somebody? What is the area of this graph, this section? What is the area? Yes?
Of which part, Mwalimu?
Oh, you are not concentrating. If you are not concentrating, I'm talking about the area of this part. What is the area? The part I'm shading right now.
WL over 4.
Very good. It is W
L over 4.
L over 4. How did you get that? W over 2 multiplied by L over 2. So this is equation 2. So when you are asked to compute the max, so that will be the maximum. At this point, the moment will be WL over 4. At that point, it will be WL over 4. Just allow me to just pick this call. At any point that we've been asked to calculate the design moment M, you do not need to redraw the shear force and the bending moment diagrams. You just need to use the formula that we just derived. Okay. The second situation that we are going to to derive for, let me just have another slide. Okay. All right. The second one that you're going to design for is number 2. Sorry, actually kitu acha nitoe tu. The second one that we're going to design for is we're going to design for a simply supported beam with a UDL. Okay, a simply supported beam with a UDL. How would that look like? This is a simply supported beam with a UDL. A UDL will be given as load per meter run. Okay, it will be given as load per meter run. So for instance, this will be given as a load per meter. Okay, load per meter. So, and we are saying that a UDL will act at the center of gravity. I know when you did the properties of sections, you are able to determine the specific center of gravities for different shapes. So, first of all, the first thing will be to convert the UDL load to a point load. So, and how do you do that? If you've been given that this load is load per meter run, so what will you do? You'll just say load multiplied by the L meters. Okay, L in meters, the span. So this will give you a big W. Let me call it a big W, capital W. This one is a small one, this one is a big one. So in other words, this is now a point load. As somebody is not hearing me, acha niingie kwa hii simu nikuwe na monitor because I can't really see what's happening in the chat. Okay, or you can just unmute and say something. If wewe kuinua mkono ama nini? Ayub, yes.
Mwalimu, I have a question.
Yes.
Why do we use W times L over 2 squared?
Oh, you're asking where do we use W L over 2 squared? You are coming. I can see that you have an idea of what we are talking about, and you'll actually realize that we might be using it here. Ayub, we might. Yeah, so just be patient and see how that magic will happen. Okay, all right. So how do you go about that? So we convert it to a point load, and then we are saying that we now need to find FV, meaning we find reaction at A and reaction at B. How will we get the reaction at A and the reaction at B? Okay, so somebody, Ayub, I think you have an idea. Can you try to answer that? How will we get RA and RB? Yes?
It will be W times L over 2 squared.
Why have you squared it?
Because we assume that the UDL acts at the center of the reaction occurs in between the two supports.
Okay. Okay, let's see that. Let's see that. Let's see that. Anybody else that has something? Let's see. Let's see how that would be. So if we, as Ayub is saying, that the UDL, when we convert it to a point load, it's going to act at the center. So it's going to act here. But now it is WL or W. Okay. At this instance, it's WL or W. So we'll have L over 2, L over 2. We'll have a reaction at A, the one we want, and a reaction at B. So if it's acting at the center, it means that the loads will be distributed equally to the supports. So we will have, you divide, we'll have WL. So reaction at A will be WL over 2, WL over 2. Realize the W we are using, WL over 2. So this will be the, if it's kilonewtons, newtons, this will be the magnitude of the force reaction acting at the supports. So if we draw our free body diagram, okay, so we'll have WL over 2, WL over 2, and then we'll have L over 2. This is our free body diagram. Okay, can we now derive the shear force and the bending moment diagram from it? Let's derive the shear force and the bending moment diagram. Okay, so SFD. So anywhere we have a point load, then the value of the S of the shear force will increase suddenly. So we'll have an increase of this magnitude WL over 2. WL over 2 up to that point. Because it is a UDL, then the shear force is going to vary linearly. Shear force is going to vary linearly. What do we mean by linearly? It's going to be governed by y is equals to mx plus c. It's just going to vary linearly. So what do we mean by that? It's going to vary in this manner as I'm going to draw now. Okay, it will not be constant. Okay, so we'll have positive as negative, and then the magnitude will also be WL over 2 because it is a UDL. Okay, so we need to know that because we will not be drawing all these anytime we want to do the calculations. Then we now have the bending moment diagram. We would want to know, we said that moments are maximum where shear force is equal to 0. Okay, so we want to find the moment at this point. At this point C, let me call it at the point C. So, and we said that for us to obtain moments, then we will calculate the area under graph. That is the simplest way to do that. The area under the graph. What is the area? Or you can integrate, if you want some technical terms, you can integrate L over 2. You can integrate L over 2 with the boundaries of 0 and WL over 2. For they that want to be confused a bit. Yeah, if your screen is not showing well, just unzoom. Just unzoom. So we want to calculate the area under the graph. What is the area under the graph? Somebody? Somebody to calculate the area under that graph, because that will give us the bending moment at this point. That will be the maximum bending moment. Nani yako hapo kucalculate?
Tunahesabu half ama ni yote?
Hawezi hesabu yote because unaenda by a small change, every small change. So you want just the change caused by L over 2.
It is WL squared over 8.
WL squared over 8. Very good. WL squared over 8. So how did you get that?
This half times L over 2.
Half times.
Which is the base times height.
Yes. WL over 2, which gave you WL squared over 8. So anytime you want to compute the maximum bending moment or the design moment, if it is a simply supported beam, you're going to use WL squared. This is just like a revision for you. I expected that you remember all these. And then, because it is a shear force that is varying linearly, then the curve, it is going to vary as a curve. Okay, so you'll have negative. Okay, so that will be our shear force, our bending moment diagram. And we have seen that the design moment will be calculated as WL squared over 8. Unlike the other one was WL over 4 if it is a point load. So you can find situations where you have both UDL and point load. Okay, you can have both that have UDL and point load. So of course we can have very many situations, but we know the basic situations. Okay, we have a UDL and a point load. Okay, so this is a point W and this is W per meter. So the design moment M will be equals to WL over 4 plus WL squared over 8. Okay, let me check what is the other situation that we have. So that is a simply supported beam. I want us to now look at a fixed beam. Fixed, eh?
Excuse me, Malik, we can't see the screen.
Why can't you see the screen? Is everybody? I'm seeing the screen personally. I'm also in the class. You can see my other account right there. So I don't know what's up. Maybe who is that? Nani huyo amesema haoni screen?
Ni JDL lakini imerudi.
Imerudi? Okay. It is okay. It is okay. All right. Our third situation or case. Our third case, we're going to look at a cantilever beam with a point load. Okay? Cantilever beam with a point load. Let me have a new slide somewhere. Insert new slide, blank. Good. Cantilever beam with a point load. Okay, cantilever beam with a point load. How is that going to be? How does a cantilever beam look like? So we'll have fixed in one end and hanging on the other. So you'll have A, B. We will have, it has a point load at the end. So this is load W with a span of L. Okay, so we will have, for a cantilever beam, we will have all the reactions in one end. We'll have reaction at A, and then we'll also have moment about A. We'll also have moments about A. So we will not have moments at the overhanging end. Sorry. So we will not have moments at the overhanging end. We will only have moments at the fixed end. Okay. So how will we obtain reaction? What will be the reaction at A? This is very direct. Who will answer that? Reaction at A? You can select one equilibrium. Which equilibrium equation are you going to use to obtain reaction at A? Yeah, somebody.
Can we say WL?
W. Which equilibrium equation have you used? Back your statement so that we can be sure you are not guessing on us. Reaction at A.
It is that load times length.
Why are you multiplying?
No. It is W divided W over L.
Godfrey is guessing. You're guessing.
It's what through the span, all of it.
Godfrey, please tell me two equilibrium equations. No, it cannot work like that. Somebody else? Equilibrium equation? Okay, give me one. I'll give you the other. Hey. Nicholas, can you help the class? Yes? You what?
Nimesema juu.
Oh, wow. Okay. I'm laughing because it is elementary. I'm not laughing at you actually. But okay, let me just in passing, equilibrium equations. Okay, equilibrium equations. So we have two types of structures. We have determinate structures then we have indeterminate structures. So determinate structures are the ones that can be obtained from the three equilibrium, whose reactions can be obtained from the three equilibrium equations. What are the equilibrium equations? We have sum of fx is equals to 0, sum of fy is equals to 0, sum of moments about a point is equals to 0. So this means forces to the left is equals to forces to the right. Okay, this means upward forces should be equals to downward forces. This means clockwise moments is equals to anti-clockwise moments. Okay, so so sasa tutapataje? What would be our RA using the second equilibrium equation? If upward forces is equals to downward forces, what is RA? Nicholas? Eric? We are not going to stay here. Okay. Let me just yeah, very good, very good, very good. So we'll have the RA is equals to W. So if we draw our free body diagram, we will have AB, W. So we'll have W. The reaction at A will be W. If we draw the shear force diagram, then it means that if we have A, it is going to increase suddenly with the magnitude of W, maintain or become constant, and then decrease still with the magnitude W. This will be positive. Okay, that is what will happen. It will increase by W, then we have a span of L. Okay, all right. So what will now happen? We will have no moments at the overhanging end. So you have a BMD. We are sure this one I will not even have to do calculation to determine the moments at the overhanging end, because we have no moments at the overhanging end. So we have AB, BMD. Moments will be maximum at the support, at the fixed. You see here we have clock moments. We have moments, and that is the only area that we have moment. So how will we get the moment? How will we get the moment at this point? For us to find moment about this point, moment at this point, we can only take moments from moments about A. How will we get moments about A? Yes, moments about A, we are going to say force W multiplied by the length or the area under graph. So we will have W L, and then it's going to vary linearly up to that point. So at the overhanging end, we will have no moment. So anytime you are given a cantilever beam that has a point load, you're given a cantilever beam that has a point load, then you know how to calculate the maximum moment. It is given by WL. Okay, so the fourth case is a cantilever with a UDL. Cantilever with a UDL. How do you go about that one? Okay, so this is a cantilever with a UDL. So it has a UDL AB. So the magnitude is W per meter, and this is a span L. Okay, that's the span L. So how would you go about that? Because we know all the reaction, we will only have a reaction at the support. Unlike the other one, where it was going to be experienced at the center, this one will only be experienced at the support, because that's the only place where we have a reaction at A and a moment about A. Okay, so the loading reaction at A will be given by the load multiplied by the span L. So it means RA will be the load. All the loads will act at this support because we don't have any other support. All the loads will act at this support. That is why we are not dividing or anything. So if we are to draw our shear force diagram, we would do it like this. We have A, we have B, then if RA is WL, then we'll have WL up to this point. Okay, and then because as we increase, as we move towards the free end, then we have less load, because all the loads are being borne or bared are borne but at the supports. So we are not expecting to have loads that are being borne here. Okay, so what will happen? Because it's a UDL, then it's going to vary linearly in this manner, and this will be positive. Okay, and if it varies in that manner, then our bending moment, considering it is UDL, then moments are only experienced in one end. So moments will be maximum at point A. Okay, and how do we get the maximum moment? This is the span L. Okay, so moment will be the area under graph. How do we get the area under graph? A half multiplied by the length multiplied by WL, which will give you W L squared over 2. Very good. So you have A, you have B. So we'll have at this point being WL squared over 2. and realize that it's going to vary. This should be the maximum. So if I'm to draw something, I'll draw something like this. It does not vary linearly. It is now parabolic. This is parabolic. That's parabolic. It's parabolic. Parabolic. Okay. And it's going to be negative because this should be the maximum. All right. So that's the fourth case. So if you are to find the design moment, you just say WL squared over 2 because we want to consider the worst case scenario. If we are talking about limit state design, we said that we talk about the worst case. So when we are designing for this beam, we want to concentrate on the area that can that can easily fail by bending, and it can only fail by bending. That area is where there is maximum bending. So we want to concentrate on that. We want to check on that. That is where we are going to obtain our design moment. We can go on and on and on and on and on. What have I not talked about? We have a uniform distributed load. I think the rest you're going to will be a blend. Maybe difference will be the span. We have also a varying load. We have varying loads, though we'll not find that mostly. But if we find that, that will be your assignment. Acha hapa niweka assignment. Assignment. Deduce the formula for calculation of the maximum bending moment for a uniformly varying load. How does a uniformly varying load look like? Looks like this. So it's a UDL, but it is varying. So deduce that one. How do you obtain the maximum bending moment? Okay, so let's go back to our question now, or maybe I can leave you to write that one. Yeah, write that one for a minute. Hallelujah. Hiyo umeandika Nicholas?
Yeah, nimeandika.
Okay. So our example today, we have selected a beam of grade 275. Let me change something here. Okay. So we have selected a beam of grade 275. So a simply supported beam in the figure below supports uniformly distributed characteristic load and imposed load of 5 kilonewtons per meter each, as well as a characteristic imposed point load of 30 kilonewtons at mid span. I think we have already seen an example of this, so we already know how we will obtain the design moments. Okay, Assuming the beam is fully laterally restrained, it means we will not need to check for lateral restraining or provide lateral restraining, and also there is nominal torsional restraint. It means it is well protected against swing. Okay, select a suitable universal beam section in S275 steel to satisfy bending and shear considerations. Very good. Sasa sio swali, have you written? Can you write it somewhere so that we can just make progress? Ama you screen? No. How will you do that? How will you do that? Because I want to get out of this page. I want to move. I want to move. Just draw the diagram in your books. Wow, it's 9:09. Ukimaliza kuchora, you raise your hand. Ama you guys are not making notes. Unajua nyinyi ni wale wase ati sisi unajua sisi tuko site. Sasa unajua sisi ni watu wakubwa. Inaitwa adult learning. Okay, I'd like to believe you have done that. So I am going to the next slide. And for this case, I think I will not use a slide. Let me just use the Word document. Ndio niweze kuwa na page kubwa. Okay, file, new, just a bit. Okay, let me just select. Okay, we are now in my Word document. Okay, I want around 3 pages. Okay. So let me just draw it again here. So we have I hope you can see the screen. We have a UDL, and then we have in the mid span we have 30 kilonewtons. We have been told that the UDL is made up of 5 kilonewtons per meter dead loads. Then we have 5 kilonewtons per meter imposed load. All right. So step number 1 is to calculate design moments and shear force. Calculate the design moment and shear force. All right. So considering the factor of loadings, we said that total loading is equals to 1.4 GK plus 1.6 QK, where GK is the dead load and QK is imposed. Imposed can also be called live. Okay, imposed can also be called live load. Okay, so what would be the total loading? 1.4 into dead loads. Dead loads tuko na gani na gani? Hii 30 kilonewtons ni imposed, eh?
Yes.
Okay. So GK dead loads, so we'll have 5. What's the span? 10 meters.
The span is 10
So
meters.
the loading as a result of the dead loads will be into 5 multiplied by 10. We are converting it, isn't it?
Yes.
Plus 1.6 into imposed loads. So we'll have 30 plus still 5 multiplied by 10. So what will we get? 50 times 1.4. Mimi hapa nimepata hii ni nimepata 70 plus 50 plus 30, that's 80 times 1.6, 128, which will be 198 newtons. So the next question will be, where does this 198 newtons act? Okay, because this one was acting at the center, and also the UDL definitely will act at the center. So we'll have, if we were to draw a free body diagram, we'll have a reaction at A, reaction at B, and then we will have 198 kilonewtons. Is it kilonewtons or newtons? Or kilonewtons? Kilonewtons acting at the center. So it means if the shear force FV, which will be obtained from the reactions, the shear force will be given by W over 2. See, that's what we saw from the calculations. So you'll have 198 kilonewtons divided by 2, which is 99 kilonewtons. What about the design moment? Design moment. So we are designing for maximum bending. So since it has a point load and a UDL, okay, na tulisema aje for point load and UDL, we are going to have M is equals to WL over 4 plus W, which is a small WL squared, WL squared divided by 8. Okay. Iko sawa? All right. So we make progress. So what will we have? What's our W?
198.
let's be conscious, because we know this W is the W as a result of the point load. Okay.
Yes.
It's the W as a result of the point load, which will be 30 kilonewtons multiplied by, is it dead or imposed? It's imposed, multiplied by 1.6 multiplied by L, which will be 10 divided by 4, plus the small w, we have that one, so we'll have 5. We have both dead and imposed. 5 multiplied by 1.4 plus 5 multiplied by 1.6, close the bracket, multiplied by 10 squared divided by 8. Hiyo tumeelewa hiyo kitu nimefanya hapo?
Hapana. No.
You have not understood. Okay. So we have to consider the factor loadings. Okay. Because we cannot use, we have to consider the factor of safety, the factor loading, the design factors. We cannot just use them as they are. The reason why we have used, mnajua penye tulitoa hii, wacha niongee na Kiswahili. Hii tulitoa wapi? Point load. So we did that one, yeah? So this is for point load. These are different pen. Point load. This is for UDL.
UDL.
Ndio. Na point load yenye tuko nayo hapa ni gani?
30 kilonewtons.
And you have been told it is imposed. So when you are designing, we don't design it as raw. We design it as factored load. Okay? Factored load. So if it is factored, it means we have considered the factor of safety for imposed, which is 1.6. So that's why we said 30 times 1.6 to have it as a factored load. Then multiplied by L, which is 10, which is the span. Then divided by 4, as stated by the formula. Then the second one is the UDL, which is WL squared over 8. You saw that. W, we have two of them. 5 which is dead and 5 which is imposed. So you have to factor them. So what will happen? We say the first 5 which is dead, we multiplied by 1.4. The other 5 which is imposed, we multiply by 1.6. Put them together. Then we now multiply by 10 squared divided by 8. We good?
Why are we not using 198?
Because 198 is the total loading. This is a total loading. This is a total loading. But in obtaining maximum bending moment, different loads are going to be experienced differently. Okay, hazitazi experience kama total. Point load itakuwa na yake kivyake, na tuliona. UDL itakuwa na yake kivyake. Sawa sawa. Tukitumia 198, in other words, we are saying all of them are a point load, which is not the truth. So you have to factor them as they are. This was just for us to obtain the shear force, because shear force is experienced as it is. But in bending, each load is going to exert a different kind of moment depending on its nature. Sawa sawa. Please, let's not stay here. This is the introduction. Have you gotten that one?
We are trying to capture mwalimu lakini the challenge is coming where you told us when you have a UDL you can convert it to.
So why are we
point load.
converting it to point load? It is for the purpose of obtaining the shear force and also calculating the bending moment. But they don't act as a unit. They act independently. If we decide to draw, we are going to take a lot of time, but if we decide to draw, okay, so that you can know it's different. If we decide to draw the shear force diagram for this one, for 198, what will it be? Because this will be 99, 99. If we decide to draw the one for this, how will it look like? It will increase by 99, become constant, reduce by 99, and then increase by 99, isn't it? Sivyo ndo itakuwa?
Yes.
Do you think it is a true representation of this diagram?
No.
Because we have a UDL, isn't it?
Yes.
So it is not a true representation. It is not a true representation. A true representation would look like this. It is going to increase by 99, reduce linearly to a particular point, reduce linearly, and then increase by 99. By that, we have factored in both the UDL and the point load, isn't it? But do you see that the 99 is constant? Yeah, because shear force is contributed by all the forces. But when it comes to now the actual orientation, especially ukikuja kuona kwa bending moment, where we'll be obtaining by this, it is obtained independently. Sawa sawa? Yes. So we are not using 190. This is wrong. If we use 198, we are trying to say it looks like this, which is not the truth. Okay. So situko sawa, we can make progress.
I have a question there, sir.
Yes.
What if now we didn't include the 35 kilonewton and both in the end and the post load? What if we were given just the 30 kilonewton and it is a UDL? 30
kilonewton as a UDL.
Okay. Thank you, percent.
Iwezi kuwa UDL ikiwa center. It will be hiyo itakuwa tu point load bado.
Okay.
But if you're given it as a point load, you're just going to use WL over 4. That could be very easy.
So I have a question.
Please, can we put the questions? Okay, let's just ask.
What if it is 30 kilonewtons per meter?
So that means it's a UDL.
Yes.
If it is a UDL, then you are going to treat it as a UDL, just like we've done the rest. So this one will not be there. We'll just take WL squared over 8. And then for the sake of calculating this one, you'll just do exactly what we have done, converting it to a point load. But you don't have to necessarily make it act somewhere. So it will be 30 times 10, which is 300. We good?
So now we can use that one as a point load. That is 300.
Yeah, so that 300 now you can give it as a point load. That is for the purpose of calculating what? shear force. It is not for the purpose of calculating bending moment. Yes.
Bending moment. Nimekushika sasa.
Thank you. Okay. So I can now continue. Okay. I continue regardless. So this will be 30 times 1.6 times 10. Then you have 4. Close the bracket. Plus, open the bracket. Yeah. I open another bracket. 5 times 1.4 plus 5 times 1.6. A bracket somewhere here. Another bracket. Ama mshafanya hiyo, umepata ngapi?
Ndio 7.5.
7.5. Okay. Close the bracket. Nimepata syntax error, but it's okay. Let's use yours. Okay. 307.5 kilonewton meter. Sindio? Okay. So we make progress. Step number 2. Step 2. We talk about section selection. Tuliongelelea last time. We want now to select a section. So since we have been told to design for grade 275, it means the characteristic strength is 275 Newton per millimeter squared. Okay. So for us to obtain the section, we said we calculate the plastic modulus. Let me just show you reference that we indeed talked about that by taking you back to our PowerPoint. Taking you back to our PowerPoint and showing you. So, okay, must be here, shear selection. Very good. Yes. So we said when we are selecting the section, we said to avoid bending failure, it is necessary to ensure that the design moment M does not exceed the moment capacity. So kila section yenye tutaselect iko na moment capacity yake. So hatutaki a situation where, because we have considered the worst case scenario M, so tumechukua maximum. Sasa hiyo maximum should be less the moment capacity of the section. Inafaa kuwa less yenye hiyo section imemanufacturiwa nayo from the industry. Okay, so M should be less than MC, and we said MC is given by design strength multiplied by the plastic modulus S. Okay, plastic modulus is obtained from the table, which we are going to see right now. Okay, so if we combine these equations, we'll have a situation where S should be less than M over PY. Okay, so we select an S that is less than M over PY. So let's go back. Let's go back. Where is okay? Let's go back. Okay, sorry. So we said S should be less than sorry, should be greater than m over py. So what is our m? M ni gani? Ndio hii. These are m 307.5 kilonewtons per meter. Kilonewton meter, not per meter. Okay, because it's moment. So, and since py is in newtons, so we are going to convert that one. So it will have 307.5 times 10 raised to 3 divided by kilonewton to newton to millimeter. So this is to 6. This is to 6. This is kilonewton meter, and this is newton millimeter squared. So that's why we are doing it that way. Py 275 newton per millimeter squared. Okay, so what will we have? Hiyo mmeshika hiyo ama mtataka kuniuliza swali sahi? 307.5 times 10 raised to 6. 307.5 times 10 raised to 6 divided by 275. I have 11.8181 millimeters cubed. And realize that our table, tunaendelea pamoja. I want to go to the table now. Okay, and I have gone to the table. Let me just switch right here. Okay, so tables for use. In our table, you will see that I need to convert this onto landscape. Okay. Either way, there are way to rotate this. Hai, sasa nimeharibu. Hey, you guys. Okay, awesome. So nitafanya hivyo for all the other pictures. I could have done it yesterday. Okay. If you look at it, specifically interested with the plastic modulus, you will realize that it has units of centimeter cubic. This is the elastic, this is plastic. The units are centimeters. The units are in centimeters cubed. I've sent you the table so you can check it for yourself. I already sent you the tables. Okay. So have you seen it that the units are in centimeters cubed? So we are going to convert our units to centimeters cubed right now. So we go back to our document. Okay, go back to our Word document. So convert that to centimeters cubed. What will that be? You will have is equals to 1118.18 centimeters cubed, because 1 centimeter is equals to 10 millimeters. So 1 centimeters cubed is equals to 1000 millimeters cubed. So we divide by 1000, have that, and we don't have this small, so we are going to go with 1118 centimeters cubed. So we go and select a section that has SX just above. Select a section with SX just above 1118 centimeters cubed. Haya, si mimi niende ni select yangu, si pia nyinyi select yenu, you already have the documents. Select yours, or you can see how I select mine if you want to see how I select mine. So I want one that has tumesemaje 1118. So from this table I'm checking this column, this column, and I'm not seeing any. Hizo zote ziko 7000, 6000, 1400. Okay, better I'm going down. Let me see this one. This one I have to do the thing again. Okay. All right, let me see this. So tunataka 1118. I'm in this column 1118. So I'm seeing that if it's 1118, then this is very close. This one, this is 1280. So I've found one of them, 1280. Let me write it here. 1280 centimeters cubed. 1118. So 1190 is also good. 1118. We also have 1210. I'm seeing it here. 1210 centimeters cubed. Okay. So how do we select that section? We now come across. We come across. So for 1280, that will be 457 by 152 by 60. So 457 by 152 by 60. Then second section, 1190 here will be 406 by 178 by 60. Okay. Then we go to 1210. Where is the 1210 here? Okay, it's right here. Okay, so it will be 356 by 171 by 67. I believe that's what you guys have. And all of them are universal beams. We make progress. So after we have selected those sections, let me copy paste and bring them here. These are the sections we selected. There's no way I can bring these ones to the other table. Right? Okay. No, haiwezi nishinda ujanja. I know how to do it. I always have a way out. Very good, very good, very good, very good. So I bring it to our okay. Let's make progress. Okay, so those are the sections that we obtained. Okay. So we need to select and see which one is favorable. So something you need to know about these sections is that 457, those are the sizes. 60, 67 is the mass. Okay, we are talking about the mass per meter, mass per meter in kilograms. This one 60, 67. So what does it mean? 67 will have more weight. This is heavy. And then you'll also realize because if it's mass per meter, if you have 10 meters, this will be 70 kilograms weightier, and yet pia ina supply almost the same strength. We're also going to see that if we are going to consider weight, we are not going to go for this one. So we are going to, isn't the elimination, all these sections are okay, but we have to eliminate and go with one. So if you consider weight, we will not go with this one. If you consider the size, then maybe we are going to say 457 is this is a bit huge. This is huge. This is huge as compared to 406, and they have the same weight. So we would prefer to go with 1190 because pia haiko the extreme. 1280 is far much farther than 1118. So this is more close. So we are not wasting. We want to avoid wastage. We are looking at the economy of space, also economy of matter. Yeah, mass per meter. So let's select and say we go with the section. We select section 406 by 178 by 60 universal beam. So we have selected that one. Yeah, very good, very good, very good. So we now begin classifying. So we classify the section that we have. Classify. How do we classify? We classify based on two parameters. The first parameter of classification is strength. Strength classification. And number two, we are going to consider section classification. We can only check what we know. For now, we don't know a lot of things about this section. We just know the section, the plastic modulus. Hiyo ndo tunajua peke yake. But how will we know the strength considering the size? We have to classify it. Okay. So we had mentioned in our previous class how we perform strength classification. Okay. So the first basis of strength classification is based on the flange thickness. Okay, flange thickness T. Okay, so tukirudi kwa our nini, what do you call it, our diagram here, our table. Let me take you back to our table. Just take you back to a table. The section that we selected, what is its flange thickness? Tumechukua 1190, this one. So we come. Okay, tumekuja. So the flange thickness T will be 12.8. I don't know if you're seeing that in your end. I believe so. T, flange thickness T, 12.8. So bring it here. Okay. Flange thickness T, 12.8. Flange T is 12.8. From British Standard 5950, table 6. And for ease, I have given you that table. Let me see if it's here in the tables for use. Yes. Okay. Yeah, it's right here. So tables for use. Tables for use. Table 6. Right there, I'm showing you. I'm showing it in the screen. So if you don't have it, just look at what I have. Okay. So we are saying that the design strength, for us to obtain the design strength based on the section, we are going to consider the thickness. This is the flange thickness T. So if it is thickness that is less than or equal to 16, we are going to go with a strength of 275 Newton per millimeter. What if we could have found it's 18 or 25? We could go with less than or equals to 40, which would be 265. So for our case, since it's 12.8, then it's going to go with characteristic strength Py of 275 newtons per millimeter squared. So we make progress. So we have seen that since it's 12.8, which is less than 16, I think I should write it here so that you can remember. Since T is 12.8, which is less than 16, Py is equals to 275 newtons per millimeter squared. Yes. T is less than 16, which is 2. So we have first of all classified it according to strength. So the section classification, we now want to classify it as either 1, plastic, 2, compact, 3, semi-compact, and the highest, but we are not going to actually see it now, is whether it is slender. Okay, so we want to see that. And how do we get to do that? So still in a table I've identified here. Which table is that? I think table 9. You are going to see that we have a particular constant E, which is given by 275. It's a constant Py. So E is equals to 275 over Py. So we'll have, what is our Py? 275 divided by Py, which is 275. So for our case, E is equals to 1. So I want to take you to our table for use. Actually, it's table 7. Table 7. Okay. So just to take you here, where is it? Okay, I believe you can see it now. So from this table, we need to classify it. If it is built up by welding, first of all, we are going to say, we are going to check it, the type of element, type of section, and then the class of section. It can either be plastic, compact, or semi-compact, as you can see it here. So by then I came to realize that there are different editions of the British Standard. We have one for 1993, 1999, and then one for 2000. Well, they imply the same thing, but I have another one here that is talking about the same thing, but the factors are different. You can see this one is for a rolled section, B over T is 9E, 10E, and 15E. But for our case here, B over T for rolled section is 8.5. So that one has converted. Hiyo ime round off. This one is not rounded off. So for our section, B over T, if you look at from your table, they are saying that if it is plastic, B over T should be less than 8.5 E. Na E tulicalculate tukapata ni 1. Okay, so can we look at it in the table? Tables for use, B over T. Okay, it's just right here. So we have ratios for local buckling. We have it here. So we have selected section 1190. So it means B over T will be 6.95. Are you seeing that? Amani, I think we are seeing the same thing. By the way, you guys, you should be even sending emojis saying, oh yeah. So B over T is 6.95. So if it is 6.95 from our table 7, how can we classify it? Okay, let us use this one. So is it less than 8.5? 8.5 E. Of course, our E is 1. So B over T is should be less than 8.5 because our E is 1. How did we get E? 275 over Py. So is it less than 8.5? Yes. So it means it is plastic when we consider flange. Plastic considering flange. So I want to take it to the other diagram. I want to take us to the other. Okay. So we are going to say from, okay, this is not table 9, table 7. From table 7, we have it here. Yeah. So, but from the section tables, we saw from table 7, B over T is equals to, should be less than 8.5 if it is plastic. And we saw that from the section table, P over T is equals to 6.95. So this is plastic. So we conclude and say it is plastic. The flange is plastic. The flange is plastic. What is the other? Still from the same table. Still from the same table. We need to classify it and see that we are not only talking about the flange, we also want to check the web. If the flange is plastic, what about the web? Okay, let's see from this table, what are they saying? The web, it's saying 80. Okay, so if it is plastic, then D over T should be less than 80 E, and our E is 1. So we go to the table. So just for you to see and that indeed this one has been rounded off from this one, which is 2000, D over T should be 79. So that one has rounded off to the nearest tens. 79. D over T should be less than 79 E. So we go to the table. Go to the table. We get D over T, we see. So how you are going to perform calculations will be dependent on whether it's plastic, compact, or semi-compact, or slender. So from 1190 we can see that D over T is 46.2. 46.2, hiyo acha nisichafue sana. 46.2, this is 46.2. Yes. So if it is 46.2, what does it imply? It means D over T is less than 80. Thus, plastic. That's okay. That's good. That's good. That's good. That's good. Okay. Okay. We continue and say that when we consider the flange, considering the web. Considering the web. The web, D over T is less than 80, which is equals to, ilikuwa 49 point what? Ishapotea. Tulipata ngapi? Ilikuwa ngapi? Somebody.
46.2.
46.2, yeah, 46.2, okay. Okay, 46.2. So we conclude that it is plastic. So, therefore, section 406.178.60 by 178 by 60. Universal beam is plastic and it's class 1. Class 1 plastic. Class 1 plastic. Class 1, you can see it from this table. The first section is class 1, so on and so forth. Yeah. Whew. Okay. So after that, we have now to proceed to calculate. What do you guys think? It's already 10. Where's the class rep? Nicholas.
Yes.
What do you say?
You can continue. I'm still.
You are still
You
what?
know my code.
Pardon?
Yeah, nafikiria tunaweza endelea shule watoe maoni.
What? Tom, what do you say?
Yeah. Acha tumalize hili swali and they call it a day.
Hili swali. Tumalize hili swali. Because we have just classified the section. We have not done any calculation. So we'd use another 2 hours. Because you now have to do it slowly. But if I was doing it alone, I could have finished earlier. We now have to check for shear strength. There are how many steps? We have 1, 2, 3, 4. We have 5 steps remaining. So you guys, I want you to go and digest that. I have recorded it. I'm going to upload it. I want you to digest that one. That we have classified this section as class 1 plastic. When we meet again, we are going to do more. You know, you cannot study the whole 3 hours. You guys will forget. So I've recorded it for you. I'll upload it so that we can continue the next time we are meeting. At least when we finish this one, by the time we are finishing this one, you can now do any other. Sindio?
Yeah.
So I think that is that for tonight. But unless you have a question so far.